this video is regarding Wheatstone Bridge. It's not a regular Wheatstone Bridge teaching video. So here I'll be discussing a very interesting observation for a Wheatstone Bridge. And what is that? See, I think you must have read this question. So whenever a Wheatstone Bridge is in balanced condition, and in such situation, if I take all the resistors of same values, then what happens? The sensitivity of this Wheatstone Bridge is maximum. I mean, what in my sensitivity here? So if I take all the resistance equal, then after that, if I change any one of them, at least one of them, and even if I make a very minute change, it's like around up to second or third decimal point in the resistance value, immediately the balance condition is getting deviated. And that is not the case with any other set of resistors. I mean, you can take other resistors which are following different ratios, but for this particular case, when all four resistors are same, the sensitivity of the Wheatstone bridge is maximum. So in this video, I'll first discuss how to find out balance condition for various circuits, like one with resistors, one with capacitors, and then I'll discuss a general, combinations of different elements like capacitors and resistors. So basically, I'll discuss a general formulation to find out the balance condition in a circuit, in such circuit. And in the last, I'll discuss the application of sensitivity of this Wheatstone bridge. So finding sensitivity, that is another a very important category. I mean, that is the main point, that is the whole point of this video I'm going to discuss about here, right? So let's start it. Okay, so let me take this example of Wheatstone bridge with resistors. What I'll do, I'll find out the condition for balance situation in a very easy way. So imagine these four resistors R1, R2, R3, R4, and suppose, there is no current through the galvanometer, so definitely there is no sense of current in that. So you can say whatever current is going through R1, it will simply go through R2. In the same way, R3 directly going through R4. So if I current is entering, finally I current is leaving. V1, V2, V3, V4, these are the potential differences across each resistor, right? Now under balance situation, potential at B must be equal to potential at D. That is the reason you are getting this Ig equals to 0. This Ig, it has to be 0, right? Okay. How to write down, how to find out the situation or the condition for balanced case here? It's very simple. Upper arm mein current, it will be same, A to B, B to C. So what is current in R1? That is V1 by R1 must be equals to V2 by R2. Equation number 1. Similarly, V3 by R3 must be equals to V4 by R4. Equation number 2. And then you do one thing. From here you find out V1, which is R1 by R2 V2. And from here you find out V3, which is R3 by R4 into V4, right? Now you can just equate them, because why I'm equating, see, if you start from some potential here, and then if you go up to B, or either you go up to D, on both arms, and in both of the arms, there is a fall of potential, but ultimately you are reaching at the same potential at B and D. So we can say V1 must be equals to V3. V1 must be equals to V3, right? Also, this V2 must be equals to V4 on the right hand side, right? These two are the most important observation you can say here in order to get this Ig equals to 0. That's it. You have two equations. You equate them, you'll get R1 by R2 must be equal to R3 by R4, or R1 R4 equals to R2 R3. That is the situation we're getting, or the condition for the balanced case, right? Now, second, let's suppose you take a situation like this. You have a capacitor, you can say, okay, this is with capacitors. This is C1, let's say C2, C3, and then you have C4, right? And then you have a galvanometer here, like this. Okay, so if I connect it to some external supply like this, so what happens if it is A, B, C, D? So under balanced situation, when all these capacitors, they are getting fully charged, under balanced situation, VB must be equals to VD. But this is the balance situation का condition, right? That will give you this outcome, like Ig is 0. There is no current through the galvanometer. So this is more important, not this one, right? Okay. So during the charging, let's suppose you are talking about the transient phase, all these capacitors are not charging, I mean not charged fully yet. So whatever current is going through here, same current will pass through here in the same way like this. And how to find out current? I is dq by dt and q equals to cv. Q equals to cv. So suppose across this you have potential difference v1, here v2, here v3, v4, exclusively across the capacitors. So it is C dV by dt. That is how you can find out current. Now in the upper arm, A to B and B to C current values are same. So it's like C1 dV1 by dt must be equals to C2 dV2 by dt. Equation number 1. Then for the lower arm, C3 dV3 by dt, C4 dV4 by dt. These will become equal. Now you do one thing, from this equation you can find out dV1 by dt. So that is C2 by C1 dV2 by dt. From here you find out dV3 by dt, that is C4 by C3 dV4 by dt. Right? Now after this we know one thing, if you start from some potential at A and you're going up to B, so the upper capacitor is consuming C1, lower capacitor is consuming V3, and ultimately at B and D you're going to get same potential. So you can say one thing, that V1 equals to V3 and that V2 equals to V4. So the differential values will be also same, right? Like this. So see these two findings we did above. So dV1 by dt and dV3 by dt. So if I equate them, so it's like C2 by C1 dV2 by dt equals to C4 by C3 equals to dV4 by dt. These will also cancel out. So finally what you got, C1, C4, C2, C3. That is like you are multiplying the cross values of the resistor, C1 into C4, C2 into C3, right? Okay. Now a general relation or general condition. What kind of generality I'm discussing here? Suppose we don't know whether you have resistor, capacitor, and even you can have a combination of them or mixed version of it. So I'm drawing boxes. These boxes, I don't know what's inside them, like this. So let's say this is A, B here, C, and D, and then you have a galvanometer connected between B and D to sense the current. Okay, so I don't know what's inside these boxes. Let's suppose their overall resistance I'm representing by Z. So it is Z1, Z2, Z3, and Z4. But you need to understand the Z wala concept here. See, Z is actually called impedance. Z is called impedance. And what is this impedance? There's very interesting theory behind it. Actually, regarding impedance, you are going to study it in AC chapter, but still, let me discuss it here. You can understand it, no issues. So there are two subcategories of this, resistance and reactance. Resistance and reactance. See, if I talk about a resistor, let's say this is a resistor and some current passing through it. So how that resistance is arising? We know the funda, like those electrons are moving through the material and they are having large, I mean, a huge number of collisions with the rest of the ions in that crowded space. So it's like a jam packed. So basically, finally, because of that collision, only you're going to get this sense of resistance, right? That is how any resistor is providing obstruction to the flow of current. And resistance is like a dead property. I mean, for any resistor, whether it is, if I use it in this way, or if I flip it then connecting in the circuit, there is no effect. Its sole purpose is to resist the flow of current, right? That's why we are calling it as a dead element. Reactance, on other hand, it is a different thing. It's interesting actually. Let me take one example. Suppose you have a capacitor, let's say capacitance C, and you're connecting it with a battery through a switch, right? The battery will charge the capacitor, and what will be that maximum charge? Let's say positive q here, negative q, and you know how to find out this q, which is equals to c. Correct? Now, if I ask you whether this capacitor is charging instantly or not, so if you have already done this topic RC circuit with DC source, then you will find it very easy. Anyways, let me discuss it. So the charging is not happening instantly. There is some resistance of this wire, even though I'm not connecting it here, but still practical, there is some resistance of the wire, and even with battery you have some resistance. So if I see the overall trend, you can say once this capacitor is fully charged, the current becomes zero, right? There is no further flow of current. So if I see the overall trend of current, it initially, the moment when you switch it on, it is maximum, and then it is decaying, finally becoming almost zero, close to zero. Better to say, you can do it this way, like I tends to zero, right? Okay. Now the interesting part is, suppose if I put a curtain over here, I don't know what's behind it, capacitor, resistor, and if I see the trend of current, you can think of it like there must be something behind the curtain which is resisting the flow of charge. I mean, it is, obstructing the value of current. And that obstruction is not exactly similar to resistor. I mean, resistor mein there is fixed kind of obstruction. I mean, without resistance, if you have, let's say, 10 ampere current, and with resistor you'll get, let's say, 5 or 6, and that will remain constant. But with capacitor it is keep on changing. Correct? So capacitor is also behaving like a resistor, but we can't say it as a resistance of the capacitor. We will say, we'll give it name as reactance. Why reactance? See, reactance is something related to, reaction to some activity. So you can think of it this way. As I said, resistor आपका dead element है बेटा. It's completely dead element. There is no effect of, right and left combination. But capacitor may depends what is the value of capacitance, right? And you see the trend of current, it is keep on changing. So it's like it is something which is active behind the curtain, right? A live element. So resistor is a dead element, capacitor is a live element. Both are resisting the flow of current, but the whole physics is different, even though the names are different, resistance and reactance. So collectively we are saying it as impedance, right? That's why if I take this situation, Z1, Z2, Z3, Z4. So Z is representing the impedance. So you can treat Z as equal to resistance, if there is resistance there, plus reactance. For example, suppose within the box you have this circuit, like you have a resistor and then you have a capacitance, right? So they are going to have overall impedance here, right? But yes, unit wise you can add them because both of them are in ohms, right? Okay, so if it is Z1, Z2, Z3, Z4, then under balanced situation, we can say VB equals to VD. That is simply implying, as we did earlier, the cross multiplication, like Z1, Z4 must be equal to Z2 and Z3, right? So this is the general situation which you can use for any such kind of Wheatstone bridge, correct? Wheatstone bridge. Let me take one example. So let's suppose you take one resistor R1, and then you take a capacitance C1 here, and in the lower arm, let's say one resistor R2, and then here you take another capacitance C2, like this. Okay, and then this is A, B, C, D. You have a galvanometer to sense the current. Okay, so under balanced situation, VB must be equals to VD, and see, like cross multiplication you can do, like resistance. So on this AB arm you have only resistance, so it's simply R1, and this will have impedance. Basically it is reactance, and but I'll treat it as impedance, so it is Z2, and this will be Z1. So R1 Z2 equals to R2 Z1. But how to write down impedance or resistance, sorry, reactance of a capacitor? See, here I'm directly giving you formula. So Z of capacitance is actually represented by X. You can treat it as X. So XC. It is proportional to 1 by omega and it is also proportional to 1 by C. I'll explain it, wait. So X equals to 1 by omega C. Either directly learn this formula at this stage or we know how to find it. How? Omega is actually representing frequency of AC source. For DC, it is equals to 0. DC mein beta, you are not fluctuating the applied voltage, but in AC you are doing it. And AC may be how fast you are fluctuating it, that is given by this omega, I mean angular frequency, right? So if it is DC, in ideal situation, the capacitor is immediately charging, right? And then there will be zero current in the circuit. So imagine it this way. So suppose if you have a DC here, voltage V, and suppose the resistance in the circuit is certainly zero in ideal situation, so the capacitor will charge immediately, and immediately there will be no current in the circuit. So you can say as long as, I mean, the moment when you're pressing the switch, immediately capacitor is charging, and immediately there is no current in the circuit. And that zero current is actually representing a huge or infinite resistance of this capacitor, better to say reactance. That's why when if I put omega tends to 0, Xc is tending towards infinity. Correct? Right? And if I take AC, AC को आप कैसे represent करते हो बेटा यहाँ पे? You have capacitor. This is representing a AC source. तो AC source में क्या होता है? You're not actually fully charging. First, you are trying to charge like this, यहाँ positive, यहाँ negative, then it is fluctuating, तो यहाँ positive, यहाँ negative. So basically, you're not giving enough time to this capacitor to fully charge. So current is never going to be zero. So higher the value of frequency, it's like 10% भी charge नहीं हुआ था, immediately you change the polarity, right? So the capacitors keep on, you are fluctuating, keep on fluctuating the potential across it. So capacitor will never reach to its maximum charge state, where current becomes very weak or becomes zero. So smaller the value of omega, higher reactance, higher the value of omega, smaller reactance. And it also depends on C by this inverse proportionality relation. But this might be little bit tricky for you to understand if you haven't done AC portion. But let's say, even if you just remember the reactance value for a capacitance, which is 1 by omega C, then you can simply write it like this. Okay, so again, if I use that balance situation, what was it? R1, what was it? R1 Z2, and then R2 Z1. R1 X X2, R2 X1. X2, that is 1 by omega C2 equals to R2 1 by omega C1. So it is R1 by C2 equals to R2 by C1. So that will give you R1 C1 equals to R2 C2, like that. That will be your balanced condition for this particular case, right? So why I'm discussing this case, just to show you that for any type of impedances, you can actually use this relation, even though you have like one side you have resistance and another side you have reactances. So that is equally, you can use it here, right? And for any general case, when you don't know what exactly in these box size, you can have a mixed version of resistance and capacitors. So in general, you can write down this cross multiplication of impedances. So the whole idea behind these 3-4 examples is how to write down the balanced condition for a Wheatstone bridge. Sensitivity of Wheatstone bridge, that is the main topic of this video. Now what the theory says, if you have all resistance equal in a Wheatstone bridge, let me take, just say R, R, R and R, then see, still you have a balanced situation here, so you can say VB equals to VD. So what I did here, R1 equals to R2 equals to R3 equals to R4, all of them I'm taking R. Now what is my sensitivity here? If I change at least one of the resistor, you can change all of them, but for simplicity, I'm taking only one resistor. Let's say I'm changing this resistor. So definitely the condition of balanced Wheatstone bridge will get affected. And even if you don't take all of them equal, but they are following this relation R1, R4, R2, R3. You can choose any other pair like uh, 3 and 8 and 4 and 6. These type of resistors you can take. Even in such case, if you change any of the resistor, this balance condition will get deviated. But what is the observation? That if I take all these four resistors same, then after that if I change any one of them, in such case, even for a minute change, for what type of change, even 10 to the power minus 2 or 10 to the power minus 4 ohm, even if I make such tiny changes, this is getting affected. And it is not observed for any other case. So that the whole thing, the whole point of this video is to prove this particular statement. What is that? That when I take all the resistors same, then sensitivity of this this Wheatstone bridge is going to be maximum. Okay, now how to find out, how to gauge this sensitivity here? So I'm representing sensitivity by S, change in output voltage divided by fractional change in the resistor. This is fractional change. What is V out here? So you take B and D point, and let's suppose you are connecting a voltmeter across them. So if all of them are equal, this is 0 because B and D are at same potential. But if you change any one of them, this is getting deviated, and this VB will not become equal to VD. Definitely there will be some potential difference measured by this voltmeter. That is actually given by V out. And what is this delta R by R? That is fractional change in the resistor, right? So this formula I'll be using to find out sensitivity of this Wheatstone bridge. How to calculate it? It's very easy. So, and even for minute or tiny fraction changes, you can write it as dV out by dr by r. That is just another differential form. Okay, so V out, this delta V out, that is nothing, just VB minus VD. How to find out VB? There will be some current in the upper arm, whatever it is, same running through the, and A to B and B to C, B to C will have same current, and in lower arm you have same current for the both resistors. How to find out VB, potential at B? So let's suppose you are starting from some potential here V, उसमें से आपको minus करना है consumed by this R resistor, R1 basically, right? So current कितना है आपका? I mean, if it is 0 volt, then what is current in the upper arm? Potential difference divided by resistor. Let me take values like R1, this is R2, this is R3 and R4. It will be easy for you to understand. Okay. So from A to C, some current is passing. And from A to C, what is potential difference B? So what is that current? R1 plus R2. This is current into resistance R1. That will give you consumption of voltage across R1. तो V you are starting from, फिर इतना कंज्यूम हुआ, तो B पॉइंट पर आपको कितना पोटेंशियल मिला बेटा? V R2 by R1 plus R2. Similarly at D you'll find V R1 by, this time it will be R3 plus R4, right? Therefore delta V out will be V R2 by R1 plus R2 minus R1 by R3 plus R4. Correct? Now after that, you do one thing. I'm taking that condition. What condition? This particular condition. I'm choosing all of them as R. This was the general relation. And then one of them I'm changing by a very small amount. Only one of them. Let's say R1. So R1 equals to R2 equals to R3 equals to R4 is R. But this R1 I'm changing by little bit amount, so it will become R, which was initial value, plus delta R, right? And I'm assuming that this delta R is very less as compared to that R value. Okay, now back to this relation. So delta V out will become V, R you can take outside, so this will become 1 by, okay, in place of R1 you write it as delta R plus R, then plus R. minus that you have all taken outside R3 as R plus R, like this. Okay, so further VR, and it will be 1 upon 2R plus delta R minus 1 by 2R. Delta V out will become VR. Then above you will get minus delta R divided by 2R, then 2R plus delta R. In this relation, I'll use one thing. Delta R tends to 0 in denominator, not in numerator. Otherwise, the whole thing will be 0. So delta V out will become minus of delta R VR divided by this delta R is gone better. So this will be 4R square. Further, you can say delta V out will almost become minus V delta R by 4R, right? What is this V? This is the input voltage, whatever voltage you are applying to the circuit. I haven't drawn this, but outside you are applying some voltage to the circuit, right? It is that voltage. तो आप इसको ऐसे भी लिख सकते हो, delta V out is actually equal to minus V in delta R by 4R. Therefore, sensitivity as per the relation, what is that? Delta V out by delta R by R. So delta R by R cancelled. So just magnitude I'm writing here. It should be positive here. So it is V in by 4 because this delta R by R got cancelled, right? So this is sensitivity for the case when all the resistors are same, right? Now our target is to prove that sensitivity is maximum only for this particular case. Which case? When all of them are equal. So I'll use a contradictory method here. I'll choose that resistors are having different ratio. Let's say some K or some Mn, something, some different ratio not equal to 1. And then I will find out expression for sensitivity, and then using maximum minima concept, we can find out the condition to get maximum sensitivity, right? So that is the next part. Now let us consider a situation, for example, R1 by R2 and then R3 by R4. So this ratio is still followed. I mean, the Wheatstone bridge is still balanced, but let's suppose they all are not equal, and let's say this is equals to K. So as I said, I'll be using a contradictory method. So I'm choosing some K value. I don't know whether it is 1 or greater than 1. It may have any other value, right? So let's start with this case. So from this we can say R1 will be K times of R2 and R3 will be K times of R4. Now let us find out that delta V out. What was it? It was V. Above you can check that R2 by R1 plus R2 minus R4 divided by R3 plus R4, right? So that was the expression. Now after that, V R2 as it is, R1 ko I'm writing uh, K times, okay, first you do one thing. See, as per that, after choosing K, these will be the relation between R1 and R3. And see, now you have to change one of the resistor. Like in previous case, I changed R1. So again here, R1 I'm changing. So R1 will become R1 dash. And how it is changing? Initially it has R1 value, but now you are changing with a delta R. Later on, I'll take the case where this delta R is very small, right? So R1 now actually becomes this. First, you can write down it as KR2, or better you write it as R1. So basically, this is the initial expression for delta V. Now you are making changes in it. So R1 will become R1 plus delta R, right? So this is after the change plus R2. This was the initial expression, right? Over that, I mean, in that equation, I'm making changes. So minus R4 by R3. R3 के place पे you can write down K R4 and then R4. Let's solve it further. So R2 as it is, R1 के place पे K R2 plus delta R1. This should be better delta R1. R1 dash becomes R1 plus delta R1. So that delta R1 is representing change in R1, specifically in R1. Okay, so you can go this way, plus R2 minus R4 by K. Okay, you can take R4 common here. It will be 1 upon K plus 1. Further, so R2 as it is. So R2 you'll write it as K plus 1 plus delta R1 minus 1 by K plus 1. Step by step I'm going better. And if I take you just simplify it. So it is, uh, it will be K plus 1 whole square into R2 plus delta R1 K plus 1. That is the denominator. And R2 K plus 1, it will get cancelled out. So you're left with minus delta R1. Okay. Now I'm assuming one thing here, that this delta R1 is very less as compared to R1. Basically, you can take this delta R1 close to 0. Basically, I'm talking about those changes which are happening at second or third place of the decimal. So this delta V out will tend to this minus V delta R1, and then in denominator, this thing you can take it as almost 0. So it is K plus 1 whole square into R2. That is approximated value. Then finally, sensitivity will become, what was the formula? Delta V out by delta R1 by R1 you have to take. That is fractional change in that resistor which you are changing. Correct? So if I just take the positive value, so it will become V delta R1 by K plus 1 R2, and then you are dividing it by delta R1 by R1. So with a delta R1 you can cancel out. So finally you got V, then R1 by K plus 1 whole square into R1. R1 by R2 we have taken it as K initially. Check this. R1 by R2, that I took it as K. So finally S ka value will become V K by K plus 1 whole square under the approximation. And one more thing you imagine, you have to consider here better. That's very important thing here. See, I started with this expression, right? And this was the expression when there was no current in the galvanometer, like one current going through above and one current going through the below arm, right? So again, this expression is considering that Ig is still 0. That means जो आपने change किया है R1 में, it is actually very less. It is actually very less. So current is changing, but almost by negligible amount. But still, you are getting a sensitivity, and sensitivity is dependent on this delta V out. So delta V out has changed, but the current in the galvanometer is still tending towards 0. So a lot of approximations are there. But anyways, you finally got the solution for sensitivity. Now the real game starts from here. Suppose you want to find out the condition for S max. मुझे maximum sensitivity चाहिए. So you have to do this thing, ds by dk equals to 0. And from here, if I just differentiate it, put it equals to 0, you're going to get k equals to 1. That means R1 by R2 equals to R3 by R4 should be equals to 1. As I said, that is the proof. So once again, let me explain what exactly is happening here. In a balanced condition of a Wheatstone bridge, if all the resistors are same, and then if you change any one of them, at least one of them, and see, you are making a very minute change. See, delta R1 tends to 0. So even with that minor change, the Wheatstone bridge is quite sensitive. That same sensitivity it is not showing with any other case where the circuit is balanced, but not, resistors are not equal. They're having some different ratio, a ratio which is not equals to 1, right? So that's why this equal resistance wala case is very interesting. Well, if I talk about any conductor, it is, if you imagine it in solid state, like it is having a particular structure, and we know one thing, that resistance of any particular solid body, it is actually depending on the type of defects and even the structural design of the material. Now, there's a term called piezoelectric effect, and what's the core theory behind it? It means the electrical resistance of the conductor changes when it is physically deformed. That means if you try to stretch, compress, elongate, or twist the material, you are actually causing change at the molecular level. Right. So basically, force is creating strain, which is actually a mechanical strain, and that strain is creating change in the resistance of the material. Of course, that change is very minute, but the bridge is so sensitive that it can even sense such small changes, and you'll get uh, a, a measurable output voltage change, as discussed above. Right. So, what kind of different applications you can have? See this application. This is first, if I talk about strain gauge, but a gauge is a word which we are using for measuring something. So first one is strain gauge. क्या होता है यहाँ पे? Suppose a bridge is constructed or a mega structure is constructed, and you want to check the health of the structure. I mean, if any strains are, you are putting any strain over it, how the structure is responding, whether it is strong enough to hold it or not. So see that a truck is passing through a big mega structure, a big bridge. So if it is installed with such a device, so because of the load, there will be some strain arising, and that strain will cause change in the resistance, and hence it will deviate. It will make that circuit, basically that Wheatstone bridge circuit, to deviate from its balance condition. Since it is very sensitive, so even it can sense or measure very minute changes in the strain, right? So that's a very interesting application. Second one, like you can monitor vibration and seismic activity. So in tall buildings, especially very big mega structure, if you install such devices, so even if it is, a very small level of earthquake is there, so any minute changes in the strain will be getting, detected by this device, right? Or in dams, see, they are in continuous use. So for, I mean, after a long use, even if some cracks are arising, so if you install such devices in the dam, I'm not sure where exactly you are using them, but if you use it, so any such cracks and deformation in the material will be, detected by the circuit. That's why you can actually, it is written over that you can listen the internal crack. So acoustically you are not listening it, electrically you are listening them, basically you are detecting them. Another example, they say for most of the weighing machine, this is the whole idea. I mean, within the circuitry of that weighing machine, especially for those weighing machines which are measuring very small, minute weights like micrograms and milligrams, like that. So within the device, you have these strain gauge devices connected to balanced Wheatstone bridge. So any small change, so suppose if I'm putting any weight over the machine, so what is happening? They are causing change in the strain, or they are deforming the resistors, and they will deviate the circuit from its balanced condition. And it is getting detected electrically within the device, which you can convert into weight of the body, right? Another application, say this, you can actually use it as a pressure sensor. So basically, in mostly in any industry where, a big system is there. So suppose some part of that system is, working under a given pressure range. So pressure should not exceed below a particular value. So you can use this Wheatstone bridge as a safety device. So if I install it there, suppose pressure is going up beyond a certain limit, it will cause some, force over the container or the material somewhere where you are installing a device. So even those minute changes in the force over the wall or over the body is detected by this device, because they are designed to sense such even a small change in the strain, small change in the force value, right? So it is easily getting detected, which you can get through alarm or something. So basically it's you are using it as a safety device, right? So these are the, very interesting applications of sense using, which are actually using the concept of sensitivity of a balanced Wheatstone bridge. So that's it. Thank you.